Quick introduction for Paul. Paul worked at I'm also worked at Ball Aerospace. Paul worked at Ball Aerospace for 36 years, 25 years on JWST. We'll go through the rest of this stuff here, and I'm going to get off the stage here and give it over to him.
I wore the garb. James hat. Arranged on how to manipulate all this stuff. We'll go real quick, I told Mark, he didn't want to go into detail, real fast. My resume on the slide, I was born in Gray, Colorado. Did my undergraduate at Colorado State University, graduate work at Cornell University. Then I was a college professor for several years. Beloit College, Colorado Mountain College, University of Dallas, and then about 10 years at the University of North Colorado. While there, I also had joint appointments with NASA, or NOAA, and NCAR. And because of some of the work I was doing there, a friend of mine that I'd known at Cornell, who was a Ball, they got a program and they needed somebody who understood atmospheric turbulence. So in 1986, I went to Ball to work on the relay near experiment. A few years later, I got involved with Hubble, so I worked Hubble instruments, COSTAR, NICMOS, STIS, COS. There was some pretty exciting science that came out of those, but then we got even more ambitious, and so from our first involvement starting in 1997, I began working on the James Webb Space Telescope. Couple of stuff there. As of October 1st, I finally retired, so now I can ride off towards other horizons. What brings us together tonight? Well, astronomy. What's astronomy? The study of objects that we see in the night sky beyond Earth. Astrophysics, that's the science that tries to interpret what you see of those by interpreting the positions of the objects and also understanding the nature of the electromagnetic radiation and gravitational signals that come from those objects. And what are the objects? Well, basically, the first things that even the early shepherds sort of understood were the things that wandered relative to the stars, and that's what the word planet means, wander. So it's looking at our solar system, but also understanding our local galaxy. For a long time, we thought the whole universe was just our galaxy. And then, starting really in the late 1800s, 1900, began understanding that there were galaxies beyond our own, so we began looking and studying those. All the way back to now, understanding the cosmic background microwave radiation. But what also brings us together tonight is looking at the engineering that allows us to build the systems or the tools that gather that data that we use. So what are the tools we can use? Early people gazed at the nighttime sky, and they used measurements of positions. Was the primary source. So things like the Astrolabe, there were calendric formations like Stonehenge, many cultures, the Aztecs, Incas, a lot of them have those kind of tools. But in the late 1500s, Tycho Brahe did some of the most careful measurements using a large mural quadrant, and then what was more important, let's see if I can finish this, was this idea of the equatorial armillary, which was putting two arms to measure angles around a large circle, and the axis of that circle pointed towards the North Star, so it was in the equatorial plane. And by doing it that way, he could measure with one arm and then the other, and it would compensate for any bias errors in the measurement. So it was one of the first times of really starting to look at how do you look at your tools that you're using and remove the bias in those tools. His very careful measurements were what Kepler used to resolve the Copernican Mars catastrophe, and also led to the whole idea of the sun, that is the center of the solar system, that things don't rotate around the Earth. Then it advances even further when Galileo introduces the telescope. There have been people before him who had actually experimented with telescopes, but he was the first one to sort of look at the stars with it. He looked at the 4 moons of Jupiter. But if we move on from that, really, for astronomical work, what the real source comes is reflecting telescopes, primarily from Isaac Newton and James Gregory. James Gregory was a very quiet, unassuming Scotsman who worked quite a bit with Newton. Interestingly enough, he went to Italy for about a year or so and actually developed calculus independent of Newton, but worked with Newton at the same time. But also worked on telescopes. About the time that Newton finally actually built his telescope, Gregory had introduced his concept that actually looks closer to the telescopes of today. Instead of looking at the prime, folding the prime focus out the side of the tube of the telescope like Newton did, he actually used another concave lens beyond the prime focus and bring the light back into behind the primary mirror, which is the way many of our Cassegrain type telescopes work today. Well, a telescope makes far-off objects seem closer and larger. There's Kit Peak along with Little Thompson. And going to larger and larger apertures gathers more light to detect fainter objects. A little interesting tidbit. Here on Earth, because of atmospheric seeing, which I'll talk about later, large apertures don't help you see angular resolution any better than smaller telescopes, but they collect more light so you can see fainter objects. Well, Lyman Spitzer came along in '46 and advocated putting telescopes in space. So we ended up with things like the Hubble Space Telescope, and now we have James Webb. Why in space? Well, what I just applied a minute ago began talking about. One of them is our atmosphere absorbs a lot of radiation. It doesn't absorb that much over the visible range, and that's sort of where our eyes developed and can see in the visible range. But also, there's a little bit of light comes out in some of the infrared, the longer wavelengths. But notice, in the UV, it looks black. Not much light gets through the atmosphere, and it doesn't get much out as some of the longer wavelengths, and we'll see. We want to go all the way out to that number 30 for James Webb. And so you wouldn't be able to do any kind of measurements of those kind of wavelengths of light from the surface of the Earth. Also, the optical turbulence diffracts the light, it blurs the light. And so again, as I mentioned before, about 50 centimeter aperture is about the limit of resolution. So if you go to telescopes bigger than good binoculars, you're gathering light so you can see fainter objects, but you can't resolve the angular size of them any better unless you go to adaptive optics. Now, technology like adaptive optics to help compensate for the atmosphere that they use out of tech and things like that do allow them to see somewhat better. Also, going to space, you can see fainter objects. The background is reduced, especially when we operate in the infrared, not in the visible, but in the infrared. We all glow. You and I, if we were to look at 10 microns wavelength instead of the half a micron that our eyes like to look at, we'd all be glowing in here. And so, if you look up at the atmosphere is glowing at those wavelengths. And so if you try to look at things way out in outer space, you've got to look through this glowing, diffuse stuff in front of you. So it makes it very difficult to do from the ground. You go to space, you don't have that. So, let's look at then, how do we design a telescope like James Webb? Well, almost one of the things you learn in, quote, systems engineering and systems architecture is you have to understand what's the goal or the mission of your customer, what people are looking for, and then you start trying to sort through what are the ways that you can achieve those. Well, in this case, you have to look at what are the questions being asked by the scientists, and what are the sort of the grouping, the themes of the science that you want to look at. And so for the Webb, we looked at these 4 themes. First light and reionization of the universe. I'll talk about that more a little bit later. Then looking at how galaxies began assembling, coming down then to understanding the birth of stars and protoplanetary systems, dust debris around stars, that sort of thing. And then finally, planetary systems themselves and origins of life. So, to meet those 4 science themes, what's needed for the observatory? Well, the science goals push the spectral domain into the infrared. The spectral range is from 0.6 micron wavelengths out to 29 microns. And again, let me remind you, our eyes see roughly from 0.3 up to about 0.65, 0.7. So notice it starting where our eyes no longer work. They go out to longer wavelengths. Why? Well, the atomic spectra, if you look at the light emitted by glowing hydrogen or nitrogen or any of those things in our own sun or in atmospheres around us nearby, we see that the universe is expanding. And so those same stars that are quite a ways away and are expanding because of the ancient universe, they're moving away from us. And so we get something called a Doppler shift, reddening. The frequency tends to slow down and get longer wavelengths as it moves faster away from us. And so if we want to look at the very earliest galaxies in the universe, those are moving away from us so fast that those hydrogen emission lines that are in the UV invisible, if they were nearby, are now shifted clear out into the infrared. So we want to be looking at the infrared to look for the same atomic spectra that you would use visible if they were close by. Also, you can see through dust much better with the longer wavelengths. I use the analogy if you're ever on a foggy night and you're approaching these stoplights, and I don't know if anybody knows, but only nerdy scientists like this. Notice that you can see red when the stoplight is red quite often on a foggy night, and then it turns green, and all of a sudden you just see it disappear. And it's only when you get much closer you suddenly realize there's a green light there. The longer wavelengths penetrate the fog much better than the short wavelengths. So radiometric sensitivity, let's not worry about wavelengths now, but just how sensitive we are to seeing signals, they really depend upon collecting a lot of light. And so it really drives us to having a very large aperture for the telescope, but also we have to make sure that we don't lose much going through the telescope. So we don't want absorption in lenses or poor reflectivity on mirrors. We have to have good throughput. And finally, the goal for meeting these science objectives for James Webb was that the background would be naturally limited. There's a dust cloud in our ecliptic plane. There's, the asteroids grind themselves up and you have dust coming in from Jupiter all the way into the sun. And we're looking through that dust. And that provides a natural background. We want to make sure that we don't have other things causing background light noise that's any larger than that. But we can't get away from that. That's part of nature. So we wanted to be naturally limited by the zodiacal light. As we get up to longer wavelengths, we could, potentially get down there, except for the fact that the technology limits us there, not Mother Nature with the zodiacal light, but the fact that dark noise in the current, dark currents, reed noises, all kinds of electronic detector noise becomes the limiting factor. And so we want to get as good at detectors as possible to reduce that noise, but we only have to make sure that the stray light characteristics of our observatory are below the detector noise rather than natural when we get out to long wavelengths. Stability of the sensitivity from observation to observation drives the thermal and dynamic stability and technology for these highly sensitive IR detectors. When we try to measure just exactly how bright is something, we want to be able to come back sometime later and measure that and know that it doesn't look like it's different because our instrument changed. We don't want the instrument to change. We want to get the same answer. So it requires us to have very good thermal stability and dynamic structural vibration, etc. How good is James Webb? John Mather, who won the Nobel Prize and is a project scientist, likes to use this analysis. But the thermal glow of a bumblebee on the surface of the moon, don't ask me how a bumblebee is going to still be alive on the surface of the moon. But a bumblebee on the surface of the moon, a thermal emission just from its body heat would be detectable by James Webb if it was here on Earth. Finally, the resulting solution to meeting all these science goals is to have a telescope that's large and it's stable and cold. I mentioned that you and I glow at 10 microns. Well, if our mirrors are glowing at 10 microns, we aren't going to see very much. So we have to have the whole telescope very cold so it is not glowing at the wavelengths we want it to work with. So it needs to be cryogenic. This favors an orbit such as an L2. Low Earth orbits like HST won't work. A lot of people don't realize it, but I've just, for the scale of it, there's the Earth, and there's the height of the HST orbit in the yellow circle relative to the surface here. And so what happens is, if you want to look at some object out there, and you know, sort of in the plane of your orbit as you go around the Earth, every 45 minutes, all you're seeing is Earth. And you're getting all this heat and bright light coming from the Earth, and then you come around and you get 45 minutes to try to look at something. I worked on Hubble instruments. The instrument enclosures fluctuate by 20 Kelvin. That's roughly 35, 36 degrees Fahrenheit every 45 minutes. Not very thermally stable. So, you go 150 million kilometers. People that like miles, it's 1 million miles from the Earth. You get way out there, and now you have a very stable environment that allow you to get cold. The unique thing about the L2 orbit is the further away you get from the sun, the slower you go around. But the L2 is a point just a little bit further out from the Earth, such that the gravitational pull of the Earth, that extra little boost to the gravitational pull of the sun, allows an object out at the L2 point to go around the sun at the same speed as the Earth. And so if you put it out at L2, it goes around as the Earth goes around during the year. And you've got a nice constant relationship between the observatory and Earth. It's a saddle point. If it gets a little bit ahead, it slows up. If it gets a little bit behind, it speeds up. But if it comes towards the Earth or away from the Earth, it falls out into a drift away orbit. So it does require some fuel to put it into a stable condition. But just because you put it out where it's a long ways from the Earth, to still get a really cold instrument, you have to still do some unique engineering design. And the idea is very similar to the way you do a doer. The Nicholas instrument, I like to use it as a good example. You have the hot environment that's around the outer shell, and as parasitic heat goes into your doer, you like to intercept it at intermediate levels and catch that parasitic heat and don't let it go on in. And so you have shields. There's an outer shield that uses a radiator to catch and dump it. You go in a little bit deeper, there was another thermoelectric cooled radiator, eventually a vapor cooled, and then finally you have the cryogen, and your instrument is hooked, the classic term is a cold finger to your instrument from your cryogen that keeps it cold. Well, what have we done with James Webb? Essentially, you can think of it as sort of slicing this doer and opening it up. Here is your outer shell that's exposed to the hot sunlight all the time. As that tries to radiate in, it hits these inner layers of the sun shield. And it's hard to see in that picture, but they're separated by about a 2 degree or a 3 degree angle. And that's so the heat radiated from one shield towards the other doesn't, if they were totally flat and parallel, it would just bounce back and forth, eventually be absorbed, and the heat would slowly propagate on through. But by being at an angle, it goes through, bounces, and it tends to go this way, and this way, and this way, and it goes out the edges. And so those edges out this way, and likewise coming out towards you on these edges, radiate that parasitic heat from each layer. So it helps you be efficient. The total SPF, you'll see people talk about sun protection factor of that sun shield is 1 million. You think your sun shield is really good at 50? So what it says, for each watt of solar energy hitting the top layer, you're only getting a microwatt coming off the sun shield to the telescope. I said it needs to be big. The other thing is, if it's big, it's a lot of mass, it's more hard to get that much to orbit, so you got to figure out how to make it very light. James Webb is roughly the total observatory is just slightly over 1/2 of the mass of the Hubble. But it's got 7 times the collecting area. So there was a lot of technology and development that went into the development of these, of the whole observatory, but in particular, the mirrors. The layout, it's got a front end that looks like a traditional cassegrain. The large primary reflects it to a secondary that then reflects it back. But the problem with a traditional cassegrain telescope is that it gives you a very sharp image when you're looking right on axis. But if you try to take a picture that's got a big field of view, the further you get out in the field, it gets more astigmatic, more astigmatism. And so it doesn't give you, you can't get a very large field of view. But if instead you let it hit a tertiary mirror, and the tertiary mirror is such that any one field point only gives you a beam, just a small portion of that mirror, you can tune different parts of the mirror to correct the amount of astigmatism that's associated with that field. And so you can get to corrections that allow you to then get images over a bigger field of view that still are nice and sharp. It then goes back, it hits a flat fold mirror, but instead of trying to put all your instruments blocking all the sunlight coming to your primary, you fold it back here to get to your instruments. And each instrument has its own pick-off mirror, palm, so you can pick off different parts of the field for the different instruments. But also, that fold flat allows you to mechanically control it so that it can give you compensation for slight jitter in your observatory to hold the image very stable. So, what do we have? We've got 18 primary mirror segments, a secondary mirror, tertiary mirror, and the fine steering mirror. And how well were they built? Well, they were built very lightweight, which is a challenge then to get a very sharp, stable figure, but they were built to things that are, quote, nanometer surface figure. A nanometer, that is 1/1000th of a meter. Well, how flat is that? Interestingly enough, the size of one segment of the primary mirror compared to the radius of curvature of that curved surface that's polished into it is about the same ratio as the size of Colorado to the radius of the Earth. And so if you polished Colorado to the same flatness as one of the primary mirrors, how flat would Colorado have to be? You would have to flatten Mount Elbert and raise up the Arickaree River that runs out into Nebraska. You would have to get those two flattened out to where they're only 5 centimeters different. That's how flat these mirrors are. And people comment they're gold coated to give you very good reflection in the area. Isn't that expensive? It turns out those gold coatings are extremely thin. So even though it's 25 square meters of primary mirror, and then you've got a little bit thrown in for the secondary, tertiary, etc., the layers are so thin that the total amount of gold is 2.5 cc's. It's about like a 1/2 inch cube on the side. Yeah. The current price of gold, that would be about 50 grams of gold, somewhere around $3,000 on a $10 billion observatory. It's not a factor in terms of expense. The 4 instruments provide different functions. Wavefront sensing and control is done as part of the NIRCam. So one of the efficiencies of not having to have an extra instrument and a lot more mass for wavefront sensing and control is to figure out how to use images from one of your science instruments as a way of controlling your wavefront. So NIRCam has that role. But you also then have the NIRSpec, which does the spectrometer. It spreads it out into the spectrum so you can do very accurate measurements of the spectral characteristics of things. It also has a unique technology, which is a micro shutter array. What it does is allow you to make little slits just for certain stars in the field of view and block all the rest of the field of view. So you can get very good line spectra of different stars in one image. The fine guidance sensor, it's used primarily for the guide star, which feeds the information to the steering mirror to hold it very steady so you eliminate jitter. And finally, the MIRI, which is the workhorse in the longer wavelengths, the mid-infrared wavelengths. But to get good signal, it requires a detector that's much colder than the rest. So the rest of the observatory is cooled, the mirror's down to about 50 Kelvin, but the near-IR detectors are cooled passively with radiators to space to 35 Kelvin. But MIRI needs about 6 Kelvin. So there is a 2-stage cryogenic refrigerator on board that allows the detectors, just the detectors and ceramic area of MIRI to be cooled even further. Well, the way the telescope works, this is similar to, actually, Hubble is the same way. The telescope creates a large image, and you cookie cutter parts of that image to feed to the different instruments. So this is the layout for all of them. So, for example, if you wanted to put some unique star or region of the sky into the center of the NIRCam B, or no, actually that's NIRCam A, over on the right, you would have, this is what the field would look like in the other instruments. And in particular, you have to pick, whenever you pick what field you want in a given instrument, you need to figure out what's the appropriate star that's in the nearest field of view, in the fine guidance field of view, to use as your guide star. So there's this, operationally, there's this process of always having to look for what would be the appropriate guide star in order to achieve looking at a given target science field. The other thing that the instruments have taken advantage of is the technology development in detectors. This is just an interesting plot that shows sensitivity over sort of time compared to the sensitivity of the human eye. So just gathering more light, like Galileo did, and feeding, narrowing that light, bringing all that light down onto your eye, gives you the jump, that first jump there, right there. The blue represents the gains that were made just by going to larger and larger apertures on telescopes. But notice around 1900, we developed photography. The human eye can't integrate for a long period of time. It only sees roughly the cycle time of the retina, which is fractions of a second. But with photography, you can sit there and stare for a long time and do a time exposure. And so really faint objects, you can integrate long enough to start seeing them. And so that was the advantage of photography. Then they developed electronic focal planes. And the electronic focal planes even gained further sensitivity. And so you see that the sensitivity on JWST is 10 to the 10th times that of the naked eye. Well, it's too large to operate in operational configuration, so this just shows roughly to scale, the deployed configuration, way too big to fit in that nose cone. So it all has to be folded up into the nose cone, and then I've just shown what it looks like by the time you put it on the stack of the rocket. This is just a picture of the actual sun shield and telescope. What I want to point out here is, whoops, size, that's a person there. That's how big a person is compared to that. And that's got to be into a nose cone. When it's all folded up, it looks like this. And so notice that is, that's, you know, still big, but notice that it's not nearly as big compared to the people. And then finally the picture of dropping the nose cone down over that crew. This takes a little bit of time. I'll go ahead and take it. Some of you maybe have seen this before, but doesn't seem to be working on that computer. I'll go ahead and I apologize for that. My computer was working fine, but how many have seen that video? There's a few. There is if you go to the NASA JWST website and search on it, you'll get the video that shows the whole deployment sequence. The system hierarchy. You have the total system consists of the launch segment, which was the Ariane launcher. The French provided that. It launched out of Kourou, which is in French Guiana, just north of Brazil. There's the observatory segment. That's the portion that's actually in orbit at L2. And then there's the ground segment, which is the communications network with it. We rely on the Deep Space Network. They have large radio antenna at Goldstone, California, Canberra, Australia, and Madrid, Spain. And so as the Earth spins once a day, one of those will be pointed at L2. So 24 hours a day, you actually can be available to contact it. Actually, now that it's in regular operations, they only stay in contact for roughly 8 hours out of a day. But during commissioning, they were maintaining 24-hour contact. So in the total observatory, this just shows all the different things. I've got another one, next slide, that'll go into more detail about this degrees of freedom and control. What parts are controllable? What parts were fixed before launch? This somewhat shows the different companies also that were involved. Ball was responsible for the optical design and all of the mirrors. Northrop Grumman was responsible for the sunshield assembly and the spacecraft. And they also were responsible for the backplane assembly and the tower support. The instruments were a composite. NIRCam, the NIRCam instrument was the PI, the principal investigator, was out of the University of Arizona, and it was built by Lockheed Martin, Palo Alto. The NIRSpec was a contribution from the European Space Agency. The mid-infrared instrument was a consortium between the European Space Agency and JPL in the US. And then finally, the fine guidance sensor and the nearest instrument were the Canadian contributions. So this really is an international observatory. Another view of the active control of the system. Basically, the 18 segments of the primary mirror have 6 degrees of freedom, what are called rigid body. So we can slide them back and forth, forwards or sideways. We can also clock them. So that's the 3rd degree of freedom. Then we can tilt them this way or this way. So we have 2 degrees of tilt. And then finally we can lift them up and down on piston. But in addition, we have those, whoops, I have trouble getting that. Let me use this one. We have these strong backs from the points of the hexagon. They come up together right there, and then there's an actuator between that point that goes down to the surface of the mirror so that we can push or pull on the center of the mirror relative to the vertices to either flatten the mirror out or to curve it more. So we can use that to match the curvature of all 18. We can try to polish all 18 to the same curvature, but one of the problems with manufacturing mirrors is how tight your metrology has to be, how well can you control that to really get a match. By adding this, we found that we could match them even without the same level of control. So, in addition, the secondary mirror has 6 degrees of freedom. Actually, it's the very same design of actuators and everything else, but we can control it 6 off, but we don't have to control its curvature. And then each of the instruments, the pick-off mirrors, can be controlled in what they call a piston, essentially to adjust forwards or backwards to get them matched up with where the focal surface by the telescope is. With the exception of NIRCam, they actually have the capability of tipping or tilting that mirror as well, which helps align what they call their pupil. And then the mid-infrared does not have that control, but that's because it's at a longer wavelength, and so it's more tolerant on how well it has to match where the focus of the telescope is to still give you good imagery. The longer wavelengths has a, quote, deeper field, depth of field. How do we control then? Well, essentially, the low frequency domain control, we can control that by how we control the alignment of the secondary mirror relative to the rest of the mirrors, or we can actually collectively adjust all 18 segments to help control some of that low variation over the whole size of the mirror. Mid-frequency domain, that's where individual segments are sort of misaligned relative to each other. So we still can control that with the PMSAs, but we, so that we can try to control them to get them to behave as a single surface. And finally, the high-frequency domain, that's how good is the surface of the individual mirrors, and that's done the old-fashioned way. We polish that in before we fly it. So we do the control beforehand. And again, I just make the comparison, Colorado to the radius of the Earth comparison. So the anatomy of an active fluid control system, we have the beryllium substrate. I might comment, the blank beryllium comes in from Brush-Wellman to Axis Technologies to Lightweight, and they remove 92% of the beryllium, cutting out all those little lightweighted back. 92% of that beryllium gets sent back to Brush-Wellman to be recycled. Then we have the wiffles to spread out the structure supporting the mirrors. We use these 3-point suspensions at 3 different locations, sort of like a wiffle tree spreads out the load to pull a wagon. Then we have the 6-DOF actuators. Right there you see the actuators. Right there are 2 actuators. Right there are 2 actuators. Beryllium delta frame. And then the backplane interface vector. The beryllium delta frame sort of acts as the solid reference, and then the actuators move the mirror relative to the delta frame. And the delta frame is what gets attached to the backplane with all the rest of the mirrors. Finally, we have the handling ring. That's the surrogate for the backplane. And then we have the radius of curvature struts and the radius of curvature actuator that I described earlier. Also, to really good optical performance, not only do we have to have the wavefront air very good, but we also have to make sure that the image doesn't jitter. If we're taking a time exposure and the image is jumping all over the place, it blurs it out. And so one of the classic trades you do is how well do I have to make the wavefront air versus how well do I have to control a line of sight jitter. And this is just a plot that helps you sort of trade those out. Do you make the dynamicist sweat to make line of sight jitter 0 so the optiker can relax how well he has to polish the mirror? Or do you make them polish the mirror really good so that the dynamicist can be a little bit more relaxed on jitter? So you do those kind of trades. The fine steering mirror offload for looking at that system imaging motion. We have the line of sight dynamics on the left. We use the fine guidance sensor to sense the motion of the guide star, feeds that to the steering mirror to try to compensate it. That's the center leg. That's the line of sight jitter that we compensate with our fine steering mirror system. And then finally, we have the inter-boreside motion. The fine guider is controlling the guide star relative to the guider. What's happening over in NIRCam, those others? It turns out if the whole structure shrinks or expands because of temperature, or if the whole spacecraft sort of rolls, those can move. So there's different strategies that you can use to reduce the motion. This just shows if I control the guide star, the star down below, notice if the whole spacecraft rolls, you essentially roll that image back and forth, so you see that the star in the detector up there in NIRCam can move back and forth along that arc as the spacecraft rolls, even though you're holding the guide star rock solid. So we have to worry about those kind of things. Also, there's something called differential distortion. As much as we tried to polish that out, there's a little bit of distortion, which is plate scale. That's how big is the linear distance on the detector compared to the angular separation of two stars on the sky. And that's different for different parts of the field. So that's different for NIRCam than it is for the guider. And so if the steering mirror is controlling and holding the guide star real solid, but if it has to compensate a fairly large angle, the angle that's being compensated in NIRCam isn't the same. And so you get a little bit of this differential distortion. We uniquely take care of that by having a nested loop control system. The fine guider sees the star jitter, sends that signal to the FSM, FSM compensates that and holds the guide star rock solid. But if that is slowly moving such that the FSM is having to move to bigger and bigger angles to keep the guide star from moving, that is sensed by, we have sensors in the fine steering mirror itself that can sense that and offload that to the spacecraft control. So the spacecraft can slowly adjust to keep the steering mirror from having to move too much. And that eliminates that differential distortion. This just pictures of showing that effect. Okay, the mirror deployment, it took about a week. It was performed very conservatively. In other words, we were very careful at how we did this. And we only moved it small amounts. The mirrors for launch are pulled in and snugged against the, held in place relative to the backplane. Where they need to be for operation is they each one have to move up by about 12 and a half millimeters, about a half an inch. But they've got to be accurate to nanometers. And we have a unique design there that have these actuators that could do that. But what I meant is if it's got accurate control in nanometers to move 12 millimeters, it takes a while. Okay. So we had to watch that. Jane Rigby, who's the operational chief scientist for NASA, she's very creative. She says, we quite often talk about that the mirrors move about the rate that grass grows. So what she did is she went and bought some chia seeds and planted them in a pot the day that they started deploying the mirrors. And once we had all the mirrors fully deployed, guess what? That was about when the chia had grown and looked. And she planted them so they looked like the same hexagonal pattern of the mirrors. We were ready then for NIRCam first light. That shows the NIRCam detectors. What you really have For first light, we wanted to make sure we had light on the detector somehow, so we looked at the large Magellanic Cloud, which has a whole bunch of stars. Or was it the small? Eric, you can tell me. Large, yeah, that's what I thought, it was large. So the idea is you put it over there, we wanted to be guaranteed that we'd have light of some sort getting into the detectors so we knew the system was working. But to actually align the system, what we wanted to do was not look at where there's a whole bunch of stars like the Large Magellanic Cloud. We went to a star that's located roughly near the handle of the Big Dipper. And what's unique about that star is it's got a fairly large region around it with no other stars that are within 6 magnitudes of the same brightness as that star. So for all intents and purposes, you're looking at a black sky with one lone star. We weren't sure how accurate the telescope was pointed relative to the star trackers that control the spacecraft. You know, we wanted that to be good, but we knew that those might be off. And so when we pointed at that star, it might not land on the detectors like we thought. So the plan was to do this raster scan, you know, so that we took a whole bunch of images, moving the detector a little bit each time, so that we could cover a large area of the sky and hopefully find the image of that star. Well, it's complicated because those 18 segments don't all deploy pointing at the same piece of sky. Each segment is looking, you know, tilted off. And so that one star appears on the detector to be coming from 18 different points because they are slightly misaligned. But what the raster scan did was it located all 18, and then what you do is you tilt one segment at a time and see which one of those 18 moves, and now you know which of those 18 blobs goes with that mirror. And then you can move each of the mirrors to, well, this showed the 3 that are on the wings, 11, 10, 9 on the right wing, and 15, 16, 17 on the left wing, and the ones that are in the center. Then what you do is now that you know which segment moves which blob, you move the blobs into a fixed pattern so you can start doing some of your wavefront sensing and control. So now you can go and you move, for example, the secondary mirror, you can move that whole thing forwards and backwards, move them out of focus, greatly out of focus, better in focus. Find out how you want to align them such that you then have a good looking pattern at the end. So the entrance, they all look very different. There's a large amount of error. Finally, we get to the bottom pattern where the 0 pattern in the center looks like 18 relatively sharp images. Not nearly good enough for science yet, though. To get better course phasing, we have to stack them. This just sort of shows what happens as you move the 6 of them, not all 18, just looking at 6 right now. Move them in until you get one final image. We do that for the course phasing technique, which uses this thing called a dispersed Hartman sensor, and it can look at the difference in edge height between any 2 segments. So you'll see these little blue rectangular things. Each one crosses a gap between 2 segments. And so now what you can start doing is seeing how each of the segments lines up to each other to try to adjust them to get it flattened out. Once it was all done, interestingly enough, there's something called a pupil imaging lens in NIRCam that allows you to use the optics to not take an image of a star on the sky, but essentially take an image of the primary mirror. And so now you can see, did we have any thermal blanket laying in the way? Or how did do the struts look like they're supposed to? So this quite often is referred to as the selfie. And it's a little hard in this picture, but if you look real carefully, you can sort of see a pattern. Up here you can see a little bit of structure. And what this is actually seeing the gap between the mask that's a defined steering mirror and what we call the frill that's laying around the primary mirror out above. So it really helps you see that those two things are aligned, that you're getting good alignment of the primary mirror relative to the internal mask of the fine steering mirror. Then we did a coarse multi-field. Remember I said that you have differences in field of view. We want to get rid of those field-dependent errors, which essentially are from a secondary mirror misalignment. And so one thing was to use a Shank-Hartman process. You form the 6. We have to take one out to the side to use for the guider. But now what you do is you put those at the far corners of your detector. And then, if you flip them, notice now it's the lower right one was for the guider. Now in those up above, you see it's the upper to the left that got pulled out to use as the guider. But again, those remove the bias from left to right. And what happens is, if that pattern that's in the center is slightly different, you make very careful measurements where all 18 images are relative to each other. If they aren't at the same relative position at the corners as they are in the center, you know that you've got some field-dependent error, and you can try to correct that. And this was the quote, the coarse situation. It turns out that was good enough. When they did the fine phasing measurement for field-dependent errors, it already basically was there. And this just shows how well it compares with measurements that were done on the ground before we launched, when we did the testing down at Johnson Space Flight Center in Chamber A there. And this was the first phased image. It's a little bit overexposed, so it's saturated in the center. That's that black dot in the center. The detectors actually got saturated there. But by letting it integrate that long, it sort of sneaks something past the scientists who were worried about being scooped on any science. What do you see? 241 galaxies that photobombed that image. We suddenly realized with James Webb, wherever you look, you're going to see galaxies. It's that sensitive. This just shows a comparison with its resolution now. On the left was the Spitzer IRAC instrument. Spitzer was only a little bit less than a meter in aperture size. Now when you go to the 6.6 meter aperture size, you get much better resolution at the same wavelength for looking at the same field of view. So then in July, started releasing the early release science images. This was the first one that was released, which was at a press conference with President Biden. We'll see it later, but essentially it's looking at a deep field very similar to the Hubble deep field. But you can just see there's an amazing number of, anything that you see diffraction spikes is a point source, like a star. But the ones that are fuzzy, those are galaxies. And a few of them that have those little arcs there, interestingly enough, quite often those are from what's called gravitational lensing. So now, back to 5 minutes to finish up. Remember we had the 4 science themes? What I'll do now is just go through and look at some of the interesting science that has come out. And I've sort of grouped them by these science themes. So first light and reionization. The early release images, this was like only 2 or 3 days after early release. These are, I think those were pulled out of that early release that I just showed you. They found at that time, the record for 2 galaxies that were the furthest away. One was only about 350 million years after the Big Bang. The Big Bang was 13.7 billion years ago, and this was only 350 million years after the Big Bang. You have about 450. Just let me say, today, they have about 20 known galaxies that are more like about 200 million years after the Big Bang. This was one of the, there's a spatial program called JADES, the Advanced Deep Extragalactic Survey. This is just showing the 2 fields that they're using for that study. And I think some of the 200 million-year-old galaxies are in that Jades field. There's also been discoveries of these things called early Ps discovered. In the nearby galaxies, occasionally you see these little galaxies that they're sort of green in small fuzzy blobs, and so they're called Ps. In the far, they aren't necessarily that color. But this, again, shows that in that same field that you can pull those out, and you see some of those faint objects. Most of these, the one on the left is like 2% of the oxygen abundance of a galaxy like our own, which means it has low metallicity. That was one of the things looking for first life. Once stars have formed, and the more massive of a star, the shorter its lifetime, and it goes through a supernova. With the supernova explosion, you create all the heavy elements. The dust and debris from that former star is used then to form the next star. So you and I are recycled garbage from previous stars. But in the early universe, the stars were pure hydrogen and helium. And they were fusing and making some of the heavier elements. But you should have a low abundance of these heavier elements, or what is metallicity. And so that was one of the lodestones for looking for first life, was looking for low metallicity. And so they are seeing, like this one on the left, there's only about 2% oxygen abundance, rather, compared to galaxies much closer. So beginning to see confirmation of this idea of looking for low metallicity galaxies for the early universe. Assembly of galaxies. This just shows an example of two merging galaxies, two galaxies, quote, colliding with each other. This is the phantom galaxy, and this is interesting in showing the amount of dust, glowing dust within that galaxy. And then here's the cartwheel galaxy. The one on the left is a composite image from NIRCam and MIRI. The image on the right is just MIRI. Again, there's a, I encourage you, I'm running out of time, but I encourage you, any of these, just go do a search on your computer for these names, and you can find all sorts of interesting science that's behind these images. The spectra has confirmed the two of those funny, remember those arcs that I mentioned earlier, of gravitational lensing, confirmed that those arcs are coming from the same galaxy. And essentially what it is you have a nearby galaxy whose gravitational field warps space-time enough that a galaxy further beyond it, the light coming from it, gets lensed by that gravitational field of the nearby galaxy to bring you in. And so by looking at those arcs, you start finding out information on these very small, more distant galaxies. And you're taking advantage of nearby galaxies to give you extra power or lensing that you can't get just from your 6.6 meter telescope. Also, the spectra help characterize the composition of galaxies so that you can look at how much oxygen, neon, etc. The lack of oxygen being low metallicity for the earlier one that I mentioned. This one's an interesting one. This is a Wolf-Rayet binary, a WR binary. Those two binary stars, as they orbit, they come in close together and then they go further apart and they come in close together. And their solar wind from each one, the two winds interact with each other and form a higher density dust that then moves out as a shell. And so you see these ripples. What those are expanding shells. Each one comes from that when the two were at their closest approach orbit. And so they, sort of like on a tree, you can count rings out to tell you how long ago it was that those two stars were close together. Finally, birth of stars, protoplanetary systems. This has to be my all-time favorite for just pure art. Is the Carina Nebula, and what are called the cosmic cliffs of Carina. Essentially, Carina is not really, you see the diffraction spikes just on the upper right. You don't see it in the picture itself. But the pressure of its radiation, its solar wind, compresses different parts of the dust in this dust cloud, which causes local compression enough to then start new stars and help new stars form. And so you're seeing a lot of these. This same image, process slightly different, but it shows all the different new stars that you see in that field of view. These are newborn stars. It's quite a nursery. This is somewhere I saw a few years ago that this is probably the most famous picture worldwide. If you go and ask anybody almost anywhere in the world if they've seen a given picture, this is the one most likely to have been, that they could identify. The Eagle Nebula from Hubble, that's the one on the left. But remember I said how about infrared sees through dust much better than visible? So if you look at the infrared, you see through all that obscuring dust and you start seeing further in there. And you can start seeing a lot of newborn stars or stars being formed in those dust clouds that you just don't see in the visible. This one's an interesting one, the Stevens Quintet. It's 5 galaxies that are actually relatively close together, and there's a black hole that's driving part of their dynamics. But it's just a sort of a very intriguing image. This is a picture of the Southern Ring Nebula, and essentially is looking at the death of a star. The star, they undergo nova or supernova. This actually has 2 stars at the center of it. You see in the MIRI instrument on the right, you see them more distinctly than you do with just the single image on the left of NIRCam. But you see the expanding concentric gases that are being blown out from the death of that star. This is a star-forming region within the small Magellanic Cloud. Again, you see these, it's not some sort of just big cloud. You see these sort of filament structures of the clouds, but where and most of the star formation is in the denser parts of those filaments. And finally, the planetary systems and origin of life. We all love Jupiter, but this is just a really, in my opinion, a very beautiful picture of Jupiter. The other thing that makes this so great is all of the data from James Webb is available to the public. This was created by a citizen scientist. Not a quote professional scientist, not somebody at the university or somebody at the Space Telescope Science Institute. It's a woman out in California. She does such good work that she actually collaborates with NASA and the Institute. But this is an amazingly difficult process because it's made up of several different images from using different filters. But for them to take an image with that filter, then they have to change filters and then take another image. But what's Jupiter doing? It's rotating, it's moving. And so you're having to take all these images that don't really line up with each other and figure out how in your computer, pixel by pixel, compensate for all of that. And then compensate for color matching. What was the bandwidth of the filter? How do I adjust it to give us this artificial coloring? Because it's all in the infrared. Your eye can see this, but that's because they've translated the infrared into visible wavelengths for the picture. So just a large amount of computational effort and skill that was all done by a citizen scientist. Neptune's moons and rings. This shows Neptune and one of its moons that's very small, so small that it basically looks almost like a point source, so you get diffraction from it. But then this is Neptune itself. And there's some other moons in there, but they're a little difficult to see unless we zoom in. Now you can start seeing some of these other moons. And then if we zoom in all the way, you see the image of Neptune and the rings around Neptune. So, you know, we find that there's a number of the planets have rings. The only one with really distinctives was Saturn. So we all knew about the rings of Saturn, but there's around these others. But the big excitement, when we started architectural design from the science themes, we were told coronography is a goal, but it is not a driver for the science design. And we can't justify doing something to the design just because we need it for coronography. It was a goal, but not a requirement. But in the 25 years since we first started, exoplanets have become such a hot topic that it became obvious that coronography was going to be very important. And so we have coronographic capabilities in NIRCam, MIRI, and NIRISS. But this basically shows comparison of the coronography from NIRCam in the two lower left pictures and from MIRI in the right, but using different filters to look at it. Essentially, what it's doing is looking at that star, and what the coronography does is it has a little occulter, a little mask that blocks the bright light from the star, and you try to see the dim objects that are very near the star, but you keep from wiping out your detector with the bright light of the star. And so essentially this is showing the part that's been blocked out so that you actually then are sensitive enough to start seeing the planet. Up until now, we know that there's a lot of exoplanets around stars, but they've all been detected by inferential techniques. In other words, by looking at the dimming of the main star as the planet moves in front of it, or looking at radial velocity, how does the star react to the planet moving around it, but not a direct image of the planet. We now have a direct image of a planet about a star. Also, as the stars move past the star, as the planet moves past the star, you can see how the spectrum of that star changes as the planet moves by. And why is it changing? It's because some of that light from the star is being absorbed by the atmosphere of that planet. And so by very carefully measuring the spectra as these stars transit, as the planets transit the star, you can start getting an idea about the atmosphere. So you can start looking for characteristic molecules or elements in the atmosphere. And of course, the big interest is, are these consistent with life or not? So everybody's looking for carbon dioxide, oxygen, and methane. And finally, coronography allows us to look at dusky disks about a star, because we know that planets tend to form out of these debris disks or dusty disks that are around the stars. And this just shows an example of being able to look at the particular star called AU Microscopium and looking at its dust debris disk around it and looking at it in the different wavelengths of light. So with that, I'll conclude. I'll just say that somehow part of my message on this slide is missing. Oh, there it is. A big telescope takes a big team. This just shows a full-scale mock-up of the James Webb with people who attended the Partners Coordination meeting in Dublin in 2007. So you can see that there's close to 1,000 of sort of the lead engineers or people working on the program. But if you look at all the people who've worked the program, The estimate is there's been about 20,000 people who have in some way worked on James Webb from 14 different countries, and here in the US from 28 different states. And yes, I forgot where, I'd have to look for one. I'm in there somewhere. And with that, I thank you. And I'll take any questions. I was going to jump away from sensing and control algorithms, software. That's being used by ophthalmologists right now for studying, for the eye. Some of the other, for example, the actuators, they were designed uniquely for James Webb, but the basic principles that went into those designs are being used on a number of other programs. Even non-aerospace programs are using some of the technologies. The actuators, Bruce Hardy's here tonight, he worked much of the control stuff for, will be on the next observatory that's going up, which is the Roman Space Telescope. And it has a design where it actually controls focusing and placing of the detector relative to the telescope. And so it's using the same actuator design behind to move the detector panel around that was used for moving the primary mirror signals. And so it's using a lot of the same software and it's using the same mechanical design. Yes? Yes, since I played a very important, I'm the one to blame that did a lot of the early analysis and predicted how much we were going to degrade over the lifetime of James Webb for micrometeoroid damage. We had based that on other, some of the other systems that have flown, plus how much we really understand about the zodiacal dust cloud and the probability of those. And so we had predicted that we would get small hits, roughly once a month. The amount of deformation, wavefront error resulting from those would be small, and they could accumulate over the 5-year required lifetime and even over the goal of 11 years and not have a significant degradation to still meet all the requirements for James Webb. One of the amazing things is Arion did an exceptional job of launching this thing. So there was hardly any necessary mid-course correction maneuvers using enough fuel. So we've got enough fuel on board that it looks like we maybe can go for 20 years. But even with that, that would not add up to be below what we could meet. But, so we began seeing these things show up. We launched on December 25th in 2021. And we deployed over the first 2 or 3 weeks. And we finally began getting good enough imagery and taking those selfies of the primary mirror to recognize that there was some damage already there on the primary mirror. Some of it we probably knew about, but figured that we maybe had 1 or 2 micrometeoroids that must have hit sometime during commissioning. And we began seeing individual hits that we actually could be, we actually knew when they hit within a few hours. Just because we were taking so much data. And they were more or less what we predicted. And then along came May. And we had one hit in May that was substantially larger. So there was a spatial team put together. There was a group of us that began analyzing that and went through that. The jury is still out. We think we could probably take hits even that bad if they're only 1 or 2 a year and still survive. But I haven't been able to check. I don't know, Eric, whether you follow what has happened over the past. I know 2 months ago they were still seeing just the once a month type thing that was expected. That they hadn't been any more of these unexpected things. My guess is you can statistically show the size of the impact, the rate falls off is the size of the impact. And so you have some things that may only occur once every 5 years. Did we happen to just pick up in May of 22 one of those once every 5 years? We don't know. But it looks encouraging that we're still okay. What we did do, though, is we looked very carefully at understanding the meteors. There's something called heliometeors, which basically are meteors associated with the asteroidal dust coming from Jupiter, and those tend to come in along the sun line, anti-sun line and the sun line. Then there's a group of meteors that come essentially from the Kuiper belt, and those mostly still tend to come in the equatorial plane, but they tend to be slush balls, where the Jupiter ones tend to be little iron, mineral type particles. And then there's a group that come from the Oort cloud, and they may come in from out of the ecliptic plane. But we know the statistics on all those. The one thing that was done was look at whether or not what we might want to do is limit the amount of time that we have the primary mirror facing the ram direction, because the highest velocity particles, which tend to be the Kuiper belt type objects. So if you've got the telescope pointing down in the ecliptic plane in the direction that you're going around the sun, that's when you're at the highest risk. And so the idea is, do we want to start planning, minimizing the number of observations that would necessarily have to be taken in that orientation, at least for the first year or two until we get better handle on all this. Follow up? Yes?
The exoplanet you showed, I'm curious if you might know the approximate distance and perhaps the approximate size of the exoplanet?
Not off the top of my head. It seems to me it was about 20 light years away. But most of the exoplanets are relatively close. As opposed to all these cosmic things that are, billions of light years away. Seeing the exoplanets is looking at our nearby neighbors. The Kepler and the TESS missions, they basically are catching things that are all relatively close. Any other questions? Yes?
The question I asked was, how will that be repaired? Right?
Yes.
We need in the future to anticipate technology to be able to send a spacecraft and or unmanned out to whatever.
This is a question that haunted us since 1997. And the decision was made that the cost of manned missions were such that it made it too exorbitant to make it a fully manned mission. The one concession was that there was a grappling feature put on James Webb. So in principle, if you sent another mission that had a robotic grappling arm, it could grapple. But nothing was designed with the intention that it would be easy to figure out how to take it in or out and move it. No, energetics. It took, to get to low Earth orbit, you need about 7,000 meters per second, delta V. To get to L2, you need 11,000. So to bring it back in, you've got to slow that 11,000 meters up, down to 7,000. So it takes a lot of deorbit burn to bring it back in close, to do the repair. So most of the thinking was send a robot out to L2, but there was nothing really. The argument goes that throwaway society, even though it was $11 billion, the idea is it's cheaper to build a second one than launch with all the new technology than to try to figure out how to go repair it. And that's sort of Hindsight was the case with Hubble. I mean, we love all the stuff that we've gotten out of Hubble by having it servicing. But the servicing missions were expensive. The total expense of Hubble in equal year dollars to James Webb is every bit as much, if not more. You know, the shuttle launches used to be $500 million even if they didn't carry anybody up.